Hello, welcome back to the next video. We have this chapter. This section is putting number in perspective. So we're dealing with large numbers, and the first thing we're gonna see is the scientific notation. Right? If you know your basic math, the scientific notation was what? Representing a large or small number by a times 10 to the n power, where what? A is between 1 and 10, 1 included, 10 is excluded, and n is integer. Right, could be positive integer, could be negative integer, depends, right? So the first example we'll see is large number and small number, right? How they are goes in. Right, for the large number, we have the decimal point at the end. So move to get a small number, right? 9.1 is the digit we want, which is between what? Between 1 and 10, right? So first of all, the scientific notation, 9.1 times 10 to the certain power, right? And we move from large number to it to get the scientific notation, 3 digits, 6, 9, and the 12. All right, so we move the 12 times to the left decimal, then we get the scientific notation is 9.1 times 10 to the 12th power. Right, that is a big number. So that's the what? That is 1,000, million, billion, and trillion, right? Simply just 9.1 trillion. Right, and the diameter of hydrogen nucleus, right, is also moved the same way, right? 3 as a unit as recommended, 6, 9, 12, 13, 14, 15, right? That's 15, 3 as a unit, and we move to the right of 1, right? So 1 is included, times 10 to the, since we move from left, from a small number, we'll get a negative power. Then we have 3, 6, 9, 12, 15, right? So 15 power, right? And the molecule or hydrogen molecule, the diameter is 1 times 10 to the negative 15th meter, or usually if it's 1, we could omit it, right? Just 10 to the negative 15 meter. If it's not 1, then we have to keep it, right? That's what the scientific notation is. Right, then we see other examples about it. Right, the application where we use this type of notation, right, is in the large scale or extremely small scale. Right, that's fusion power. Extract all the hydrogen from water, use it for fusion. How much water will we need each minute? Each minute to meet the energy needs, right? Given that the annual energy consumption is 10 to the 20th joule, and the fusion 1 liter of water provides 7 to the 13 joule, right? So they are asking for what? How much water would we need each minute, right? So what? So what it requires, the final unit is what? Is certain amount of liter per minute at the end. What we provide is 1 liter of water can do that much joule and annual joule, right? Annual is 10 to the 20th, right? So given is the order half is 10 to the 20th joule per year, right? Let me put it in black color, right? So given is what? That water annual energy is 10 to the 20th joule for 1 year. So the final unit is minute, right? So we need to do a conversion from year to minute. And also what? Also 1 liter of water provides 7 times 10 to the 13 joule energy, right? So the numerator, we need the unit liter, and given is joule and liter per joule, right? So when we use multiplication, we're able to actually get the unit, right? So it seems like 1 is on the top, 1 unit is on the bottom. They will be able to cancel out, but also we need to find the unit for the year, right? For the time, for the bottom. The top look like when multiply these two, get the unit liter left already. But for 1 year, how much or how many minutes is that, right? So 10 to the 20th joule per 1 year multiplied by 1 liter of water needs 7 times 10 to the 13 joule, right? 1 liter provides that much. Then the only thing left over will be from year to minute, right? Ideally, or apparently 1 year, that we could assume normally 365 days. And from day to minute is still not that clear, but 1 day is 24 hours. And 1 hour is 60 minutes. Right, so for the unit conversion, it's always like that, right? The unit relationship is 1 bottom, 1 top, that will be canceled, right? So converting from year to days, and if we put the smaller one from days to hours, you could put multiplication, a day on top and hours on the bottom. Then if you know 1 hour, 60 minutes, that put hour on top, the minutes on the bottom, right? So when we can see, right, multiplication is able to cancel the like term, right? Cancel the like term. So we have joule and the joule be canceled. 1 year of year, days with days, hours is hours. The unit we have on the top is liter. Unit we have bottom is minute, right? That go back or converting to the amount we need. Right, that converting to the amount we need. So finally, we just take all the product, right? Everything times 1, that's whatever, just the same thing, 10 to the 20th liter. The bottom 1 times 7 times 10 to the 13, multiply by 365, multiply by 24, multiply by 60, and the unit at the end is minutes, right? The top is 10 to the 20. The bottom, right? 7 times 10 to the 13, 365, 24, and 60 are the product we need to find using our calculator. 7 times 10 to the power of 13 multiplied by what? 1 year, 365 days, 1 day, 24 hours, 1 hour, 60 minutes. Right? Is that what we have? 365, 24, 60. Yes, that's right. So we have 3.6792 times 10 to the 19th power. Right? Unit is liter per minute. Right? Finally, we just divide them. Right? It's like the power cancellation, right? It's just 10 divided by 3.6792. Since 10 to the 20 is like 10 multiplied by 10 to the 19th power, right? 10 to the 20th power is just 20 of the 10s multiplied together, right? So we have 19 of the 10s able to cancel, only one left over 110. Right? So it's 10 divided by 3.6792. Well, if you want to verify, that's 10 to the 20 divided by 3.6792 times 10 to the 19, right? It is actually the same thing, right? So 2.717, so on. 717. Seven one seven nine eight two blah 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 liter per minute, and what? And they could keep the digit of decimal, right? Look like here we have only the whole number missing, but actually the rounding of number maybe not that crucial, right? You could keep one digit of decimal or keep as whole number, doesn't matter, right? If you want to keep like 2 digits decimal, it's also fine. I will here just do 1 digit. It's 2.7 liter per minute. That will be good enough for the needs, right? For the enough energy needs. But still 2.7 liter every minute is a lot, right? Right, that is one application we use. But the key thing here is to know your final unit and to know what is provided. Right, for the numerator, you want to cancel out, put the seeking unit with the unit and put the unit you want to cancel in the opposite one. Right, so when you want to cancel the joule, you put joule on, you have joule on top, then you have put joule on bottom. Then able to cancel. It has the liter on top left over, that's good. Right, for the bottom, it's need to convert from year to minute. So you have year originally provided on the bottom. That is multiplied by the unit you want to cancel on the top, right? Year to day, day to hour, hour to minute. Finally, we'll have left over the minute on the bottom. Okay, so that's what is provided. All right, the next one, right? The next one. The distance from Earth to the Sun is about 150 million kilometer. Diameter of the Sun, 1.4 million kilometer, and diameter of Earth is 12,760 kilometer. Put the numbers in perspective by using the scale model of solar system, 1 to 1 billion scale. All right, so which means converting each 10 billion meters is 1 meter into your model, right? You have a model in front of you that's representing the solar system, and imagine how large you can build the model. And provide here is 1 to 10 billion. So every 10 billion, the distance represent, right? In your model you want to build, that you need to put a scale of 1 meter. Right, so let's see some basic. All right, let me just draw it. All right. Basic is what the unit conversion meter is the unit of standard, right? Maybe you have heard of decimeter, centimeter, millimeter, right? 1,000 millimeter is 1 meter. 100 centimeter is 1 meter, right? 10 decimeter is 1 meter. 10 to the third meter, which is 1,000 meter, is called a kilometer. 10 to the 6 is a million. It has a special name, but just put million for now. 10 to the 9 is billion. And 10 to the 12, of course, is trillion. Right, so we have a unit scale of million, have kilometers, and 1.4 million kilometers. That has other names, but we just use those things for now. Right, so 3 things need to convert, right? From distance of the Earth and Sun to the scale of the model, how large we're gonna build it, right? So first of all, distance. On the scale, right? Distance on the scale. Originally, that's 150 million kilometer, right? Kilometer. And when we convert to the scale, right? Sorry, I need to draw a better line. Okay, all right, good, a little better. Right, in the 10 billion scale, right? Use our scientific notation, right? Not yet, but unit converting first. 1 million is million is 10 to the 6. Kilometer is what? Kilometer is 10 to the 3rd meter. 10 billion in the scale is billion is what? 10 to the 9. Right, so we have 10 to the 3rd, 10 to the 6, and 150, right? That 150 is 1.5 times 10 to the 2nd power, 10 to the 6th power times 10 to the 3rd power. Well, if you can see from this step already, you're good. If not, let's just do that together, right? 10 to the 10th power. Right, so the numerator, we have the 10 to the base, and the power we could add together, 6 plus 2 plus 3, that is 11. The scale for the model, 10 to the 10th, right? So when we divide, right, same base, we subtract the power, that's 1.5 times 10 to the 1st power. Right, first power is just, first power of 10 is just 10, right? That we get 15 meters. Right, so that's the distance of Sun to the Earth in our model we built. That will be 15 meters to represent those distance. Similarly, diameter of the sun on the scale, it should be what? The same way doing, right? Million kilometers. Right, that's 1.4 million kilometers divided by 10 to the 10th. Right, so we have what? We have 10 to the 9th over 10 to the 10, which we subtract is 1.4, 10 to the negative 1, 0.14. Right, and we know it. We know each 1 meter is 100 centimeters. So if we multiply 0.14 by 100, we get a whole number, right? 2 digits, that's when we multiply by 2 zeros. That's good. And that 2 zero give us the unit of centimeter. So that is what? 14 centimeters. Similarly, the diameter of Earth you can do, right? That's 12,760 kilometer. Divided by 10 to the 10. Right, that's 1.276, 10 to the 7 power, right? If you double check, you can find that, right? 10 to the 10th. 1.276 times 10 to the negative 3 meter. And if you multiply by 10 to the 3rd power, you get only the first part. Well, how do we multiply the 3rd power? Is unit conversion of the first one, right? The 10 to the 3rd power of millimeter, that's 1 meter. Right, so we get 1.276 millimeter is the distance of the Earth, diameter of the Earth. Right, that's the diameter of the Earth. All right, the next example, similar idea, right? The distance from Earth to nearest stars of besides the Sun is about 4.3 light years. From 1 to 10 billion scale, how much far is the star from the Earth, right? So the distance is 4.3 light year. And what we know, the light year is the distance the light can travel in 1 year. That's 9.5 times 10 to the 12 kilometer. So on the 1 to 10 billion scale, right, what do we say? What do we have? So in the factor of the scale, right, distance, that is 4.3 light year. And each light year is 9.5 times 10 to the 12 kilometer. And the scale we have is what? 10 billion. Right. So we have 4.3 light year. The unit is canceled. Right? the unit of the light here is canceled. Then left over the unit of kilometer. The unit of kilometer, right? Times 9.5, 10 to the 12 kilometer. And the bottom is 10 to the 10th as a scale. Right, so we find the top 4.3 times 9.5 times 10 to the power of 12. And that's 4.085 times 10 to the 13. Kilometer over 10 to the 10th. Right, it's 4.085 times 10 to the 3rd kilometer. Right, that result you can keep as what? 4,085 kilometer is what you can do, right? Right, or that equal what? 4.085 10 to the 3rd, and also kilometer is 10 to the 3rd meter, right? Can put is 4.085 times 10 to the 6th meter, right? That's million meter. Right, nothing wrong. You can put 4,085 kilometers, can put 4.085 times 10 to the 6 meter, or you can put put that, or you can put 4.085 millimeter, right? All the things are not wrong, right? We cannot say they are wrong, right? Or they're all right. Right, and dealing with uncertainty, that's the next unit. Let's see. Right, it's asking for errors, right? The random error occurring because random and inherently predictable events in measurement process. Systematic error occurs when there's a problem in the measurement system that affects all measures in the same way, such as making them all too low or too high by the same amount. Well, that type of random and systematic error you can see is, for example, right? So the nurses want to weigh the weight of the newborn babies, right? The weight of newborn babies. The random error is occurring like when the scale is right there and the baby lying on the scale is like shaking, right? It's moving all the way. You cannot keep the baby quiet for like a single, maybe 5 or 10 seconds, right? Sometimes it's hard when they're doing something uncertain. Right, so the scale is like keep shaking, and it's hard to read an actual value, right? That is the random error occurs, right? Every baby goes onto the scale. You cannot guarantee if they are moving or not moving, how they move, how they are affect the data you read from the weight, right? So that's random error. Systematic error is, for instance, you weigh a certain object, I weigh a certain object, many different objects together using the same scale, but you're recording the number, right? But at the end, the scale, when it's empty, it doesn't show a 0. It may be when it's empty, it shows a 4 gram over there. Then every object you weight, that's 4 grams more than the actual value, right? Than it's supposed to be. So that type of thing is called a systematic error, right? That's the error the measurement system itself having, and it affects all the measurements the same way. While the random error we see before, right, occurring randomly, it doesn't have fixed value how it's being errored. Right? So that's the two types of error, random and systematic. All right, let's move on to the next. Right, the absolute error describe how far a measurement or claimed value lies from the true value. Right, the absolute error is measurement value minus the true value, and the relative error is 2c, right? Compares the size of the error to the true value. It's just similar as what we find the thing before, right? The thing before is relative change and absolute change. Here, nothing else changed, but actually the thing is the error caused by the measurement. Right, absolute and relative error in each case. True weight is 125. The scale is 130. True and the scale. So absolute error is the measured minus the true value. Right, measured was 130, true value is 125. That is what? 5 pounds of the absolute error, which means the measured one is 5 pounds more than the true value, right? Then also the relative error. That is the error, absolute error, divided by the true weight. Right, we'll get a division to get a decimal, then convert. Right, so 5 divided by 125, that's 0.04. And when we convert to percentage, multiply by 100%, we get 0.04 times 100 is 4%. And so the scale is 4% more than the actual weight. Right, the second question, government claims that the program cost 49.0 billion, but the audit shows that the true cost was 50.0 billion. Right, so the true value is 50, the claimed or the measured or the claimed cost was 49. So the absolute error, that's what? That's the measurement, measured value minus the true value, or claimed value in this case, right? It's no more the measured value is the claimed value. Where what? Where the claim value was 49 billion. The true value was is 50 billion. In that case, that will give us a negative 1 billion. Right, that means what? That means the claimed value was actually 1 billion less than the true value, right? Than the true value. And the relative error, that is the absolute Comparing to what? Comparing to the true value. Our absolute error was negative 1.0 billion. The true value cost here is 50 billion. So we have the billion cancel, the money units cancel. That's just 1 divided by 50. 1 divided by 50, I believe is 0.02, yes. And when multiplied by 100%, that is negative 2%. So that is the absolute and the relative error. And look like it's the end of the chapter 3. All right, so still again, right, if you have any question, you can going over it, and you can see also the homework assignments. All right, thank you.